guess I'll title this, this is questions asked from 3.4. So these would be maybe the challenging problems or the tough ones from 3.4. So first one, simplify e to the ln 5x plus 2. If this question is being asked, which it was commonly, in fact, the next two slides are like this too, I have to question where are we on our understanding of what a logarithm is. The logarithm, this ln 5x plus 2, that is log base e. So if I asked you what is this, I would hope you would say that this is the exponent that would turn e into 5x plus 2, because a logarithm is an exponent that turns its base, this case being e, into its argument being 5x plus 2. So take a look at what we have here. We have e raised to the exponent that would turn it into 5x plus 2. E raised to the exponent that would turn e into 5x plus 2. This is our e harmony case. This is exactly what ln 5x plus 2 wants to do. It wants to be here. And if it is there, it turns e into 5x plus 2. And that is it. It met its perfect match. This thing was just wandering around aimlessly in life, looking to attach itself to here so I could turn that e into 5x plus 2. So 5x plus 2. Likewise, this ln x squared, if we think of that as log base e of x to the second, this is the exponent that wants to turn an e into an x squared. A logarithm is the exponent that wants to turn its base into its argument. So it wants to turn e into x squared. This thing would love to live its life out, or this thing I should say, would love living its life out just wandering around aimlessly. It would love to be able to be right here. Well, guess what? It found its soulmate. So it is going to turn e into x squared. This is just x squared. These are inverse functions of one another. We start with x squared, we let ln do its thing, we put that on as an exponent on e, and we turn back into x squared. So once again, we have a case, another asked question today. We have a case of ln x cubed, which is just log base e of x cubed, which means this thing is the exponent. It would go right here, if it could find its soulmate, would go right here and turn that into x cubed. Well, in this case, lucky this guy found its soulmate. It is an exponent on e, so it's going to turn that e into x cubed. So those first three problems are just based on, do we really understand what a logarithm is? I expect everybody right now knows the words behind it, knows, oh, an exponent or a logarithm is an exponent that turns its base into its argument. Do you really know what it means? We probably aren't quite there yet if we're asking questions on this one, but that's okay. We've got time. So those three probably worth reviewing if you were interested in any of those. Okay, here we're to find the exact value of the solution. Actually, that's my modified instruction. The book just says round them to 3 decimal places, but I'm going to go for exact solution. I want to get t equals exactly what it is, and then I might leave that up to the viewer to go ahead and enter that value in the calculator. So this is an equation. We have 3 types of equations which ultimately involve logarithms, and one of those types is exponential variables. And what we are to do is to isolate the exponential, and it is isolated. I want to make a point on this. If I had an equation like 2 times 3 to the x equals 6, the exponential is not isolated. We would want to first divide that by 2 and get 3 to the x equals, in this case, 3, so kind of a boring problem. But we want to isolate the exponential. That would be its base. and its exponent. Since it is isolated, I can now take the log of both sides and proceed from there. So I'm just going to use natural log. ln 5 to the negative t on 2 equals ln 0.2. And why would we do that? Well, how do we solve for a variable when it's in the exponent? When I take logarithm with a variable exponent, I can pull that exponent out front. And I get negative t on 2 ln 5 equals ln 0.2, or negative t on 2 equals ln 0.2 divided by ln 5. And then if I multiply both sides by negative 2, I get t equals negative 2 ln 0.2 on ln 5. And that is the exact answer. And I would like to think from that we could all go to our calculators, enter that in our calculator, and get our answer to 3 decimal places. Another problem, very similar, a little uglier, but in this case, I still have the exponential isolated because the base is this big guy, the exponent here, so I'm ready to take logarithm of both sides. So ln, or log, 1 plus 0.1 on 12 to the 12t equals 2. Whoop, sorry, equals ln2 because I took the ln of both sides. ln2. Then the reason for doing that is we can pull the 12t out in front, make it a normal old number. So 12t times this mess, ln 1 plus 0.1 on 12 equals ln 2, or let's go for the whole solution now. T equals, it was ln 2, I need to divide away a 12, and I need to divide away my mess. ln 1 plus 0.1 on 12. So there is our exact solution for t. Again, I would expect that we could go ahead, enter that in our calculator, and round that to 3 decimal places. Let's talk just a second about what's going on here. This should at least look a little bit familiar. We have a formula that says the amount we end up with equals principal, what we started with, 1 plus the rate on the number of compounds per year, raised to the number of compounds times time in years. That's our compound interest formula. Well, what's missing here is p, but what if I put a 1 here? What's the story problem that would lead to that as getting us into our solution? It would be looking for t. How long would it take if we invested $1 for it to become $2 if the rate was 10% and it was compounded, or n, it was compounded monthly, n equals 12? Or how long would it take an investment to double at 10% interest rate, compounded monthly? So the answer you get to this may be of some interest to you. Hope you can find a 10% investment right now in this current economic climate. Okay, find the exact value of the solution around the 3 decimal places. Same problem. I'm glad this is part of what we're working on, though. Is the exponential, the base and the exponent, isolated? No, because the base to 0.02x is just e. So the first thing we need to do is divide away 250. Divide both sides by 250. And I get e to the 0.02x equals 40. And now I can take the log or ln of both sides, and I would suggest it'd be crazy not to do ln on this one since we're working in base e. So ln e to the 0.02x equals ln 40. But this is the exponent. that would turn e into e to the 0.02x. It's 0.02x, or you could pull the variable out in front, or the exponent out in front, 0.02x ln e, and certainly we ought to recognize what's the exponent that turns e into e1. So this is ultimately 0.02x equals ln 40. So we divide by 0.02, and there is our solution for x. Common mistake would be to, when we divide by 0.02, to have written that as ln 40 on 0.02. We're not dividing 40 by 0.02, we're dividing the whole side by 0.02. So that would not be good. And once again, round to 3 decimal places. We should be able to go to calculator with that at this time. Okay, solve algebraically. Well, these look like a mess. Round to 3 decimal places. Once again, I'm just going to find exact answers, not rounded. These look like a mess until a little bit more inspection is given. This has a factor of 2, 2. This has an x factor. This has an x factor. They both have factors of e to the 2x. So I'm going to factor out a 2, an x, an e to the 2x, and I'm left with just an x plus 1. So I've got a factor of 2, a factor of x, a factor of e to the 2x, and a factor of x plus 1. So either 2 equals 0, or x equals 0, or e to the 2x equals 0, or x plus 1 equals 0. One or more of those must be the case. Well, 2 is not going to equal 0. X could equal 0. There's a solution. Can e to the 2x equal 0? Can a positive number, e, be raised to a power and get 0? Nope. And my other solution, sure, x is negative 1. So I guess I will come up with rounded to 3 decimal places because those work out very nicely. All right, so factoring is our friend in this problem. Let's take a look at another problem like that. And now that we got some hints from the last problem, maybe we should probably try to factor this. I can factor out an x, and I get x times 2 ln x plus 1 equals 0. Excuse me. So either x equals 0, or my other factor, 2 ln x plus 1 equals 0. So x equals 0 is a solution. How about this? Ln x equals negative 1 halves. That is a sum logarithm problem. In other words, this is base e. I've isolated the logarithm. I now want to use definition log. So this, which is negative 1/2, is the exponent that would turn e into x. So my other solution is e to the negative 1/2. That again being the exact answer the book directions ask for, round to 3 decimal places. We certainly could enter that in our calculator and arrive at our solution. Okay, I think this is wrong. Find the time required for, I don't think that 4 should be there in the book. That was supposed to be a dollar sign. Find the time required for a $1,000 investment to double and triple for a given rate compounded continuously. Compounded continuously. Amount we end up with equals P times the principal times e to the rate times time. So I want to start with $1,000. I want to end, if I'm going to double, with $2,000, e to the r 0.075 times t, and I want to solve for t. So the first thing we need to do, this is an equation with a variable exponent, is isolate the exponential, and the base is just e. So I need to divide 1,000. And take a look at this. What we realize is it's going to take just as long for $1,000 to turn into 2,000 as it would take $1 to turn into $2. They could have just as easily said how long it takes an investment to double. So at this point, we should take the log of both sides to get the variable out of the exponent. I'm going to use ln, of course, because we are base e. And that frees me up to write ln2 equals, pull this guy out in front, 0.075 t times ln e, but that is the exponent that turns e into e, 1. And I end up with t equals, I'm not dividing 2 by 0.075, I'm dividing all of it, ln2 by 0.075. And that is the exact answer for doubling. So how about B, tripling? What did we just learn here? I could put in 1,000 and get out 3,000, but I could put in 1 and get out 3. I get out $3 when I put in 1, e to the 0.075 t. ln both sides. ln3 equals 0.075 t times ln e when I pull the decimal out. ln e, of course, is 1. So t is ln3 on 0.075. How long would it take to quadruple? I know that's not being asked. That's where we turn being a math person into a science person. And we say, let's make a conjecture here. Well, double ln2 on 0.075, triple ln3, I suspect to quadruple ln4 on 0.075. I think probably the book should ask you maybe to get 4 times the investment, 10 times the investment, so we start seeing those patterns occur. All right, let's move on. Oh, that is it at this time. Maybe worth looking at again, but those were the common questions over 3.4. Hope that's helpful. Let's make certain we are prepared for this coming week's test.